Well, hello everyone. Uh, this is a new chapter. This is chapter 4. In fact, it's the last chapter of this course, and it deals with exponential functions and logarithmic functions and their applications. So, the homework for section 4.1, exponential functions, is split into two parts. Part A basically is an introduction to what an exponential function is, how you can graph them, do transformations, and compare two or more exponential functions, and also how you can find the formula for an exponential function by looking at just a graph of one and knowing one of its points, just the coordinates of one point on that graph. So let's begin with an exponential function. So here is our first one. This is an example of an exponential function, 2 to the power of x. You can also have things like a third to the power of x. And you can have 5 times 1.1 to the power of x. Essentially, what an exponential function is, if you wanted to say what would the general basic exponential function look like, it would look like that. A to the power of x. A is called the base of the exponential function. And in this case, that guy up there, x, well, that's x is called x1. So in this example here, the base would be 2. In this case, it would be a third. In this case, that 5 is just a vertical stretch, so it doesn't really matter, but this is the base, 1.1. And there are some features about an exponential function, what is allowed and what's not allowed. So here's the first one. A, the base, must be positive. So you can't have, for instance, a function, look at it in any meaningful way. Let's say that guy. Now, the reason why it's not really considered a normal, proper exponential function is that the base here is a negative number, and it's -3. And you might think, well, that's not a problem, -3 to the power of 1, -3 to the power of 2, as long as x is a positive number, or even an integer like -7, you could get an answer. That's true, but you do have a problem. For instance, if you wanted to evaluate this function at a half, because it would be 2 times -3 to the power of a half. Now we know fractional powers are the same. Well, a fractional power of a half at least is the same as a square root. And there's your problem. That's not a real number. And we only deal with functions whose values are real numbers, not complex numbers. So that's our first very important rule, is that the base of an exponential function must be a positive number. It can be a fraction like a third. It can be a decimal like 1.1. It can be a whole number like 2, but it must be positive. Now, continuing on that vein, let's look at the graph of an exponential function. Well, the first thing we have to realize is that we already know that a must be greater than 0. We've explained why that's the case. Let me tell you why a is not allowed to equal 1. So the base of an exponential function is not allowed to be 1. Well, if you did make it 1, a to the power of x would become 1 to the power of x. But 1 to the power of x is 1. 1 to the power of 1 is 1, 1 to the power of 20 is 1, 1 to the power of 2.2 is 1. You basically get a horizontal line. you get the line y equals 1. And that's not really an exponential curve or function, so we won't really consider that. So we're now going to look at what does the general graph of an exponential function look like? Well, they boil down into two distinctly different situations. Each one has its own shape. The first one is when the base is less than 1. And the second situation is the base when it's bigger than 1. So let's look at this one. An example of this would be 1/2 the power of x. In this case, a is a half. Now, at this point, you're just going to trust me on what its graph looks like. And it looks like this. Well, let's look at, basically, it looks like a children's slide, at least that's how I see it. Let's have some of its properties. Well, here's one of its properties. The domain of this function, right, the usable values of x, is all real numbers, minus infinity to infinity. The range, right, the range of answers, the range of y values, 0 and anything above, but you never get to 0, because this curve gets closer and closer to the x-axis, which is a y value of 0, but never quite gets there. But it does climb upwards. Now we can also talk about what about this function, what about its x-intercepts? Well, you can clearly see it doesn't have any. What about its y-intercept? Well, all exponential functions whose base is less than 1 have a y-intercept, and they all pass through the y-axis at 1. So there's its coordinates. So it has a domain of all real numbers, a range 0 to infinity, but don't use 0, no x-intercepts, and a y-intercept at 1. Let's look at end behavior. Right. So the limit, I don't need to use the limit, let's just tell you in words, as x tends to infinity, so as you go this way, right, the y value, right, the y coordinate, becomes closer and closer, eventually 0. And as x tends to negative infinity, as you go this way, you see the y value essentially becomes infinite. Now, when we did rational functions, we had a name for a function that would level off horizontally. We would say it has a horizontal asymptote, and that horizontal asymptote, in this case, I know it's the x-axis, but you describe it in terms of the y-coordinate being 0. So that's the main features that a normal, everyday, basic exponential function whose base is less than 1 would look like. An example we used would be half. So let's do one whose base is bigger. Let's pick, say, 3 to the power of x. We'll draw right now what its graph would look like. And its graph would look like this. It's very similar in shape to this villa. I hope you'd agree, even if I have drawn it badly. But this is like the left hand, right? And this is like the right hand. They are, in fact, mirror images of each other, right? In the sense that the direction they're pointing. And this one would be a bit steeper because the base is a little bit different than this base. But the shapes are what I'm getting at here. Now let's see, side for side, a comparison of each of these properties, what the domain would be, what the range would be, x-intercept, y-intercept, essentially end behavior. What happens is x becomes extremely big and positive, and what happens to the y values when it goes negative, and it's horizontal asymptote. Right, let's start with its domain. All usable values, exactly the same in both cases. Let's talk about the range. Yeah, 0 and up, but you don't quite get to 0 because it levels off. X-intercept, they're none, again. Y-intercept, yep, it crosses the y-axis at 1. As x tends to infinity, the y value becomes huge, infinite, and x tends to negative infinity, the y value tends to 0, or equals 0, you could say. Now, the horizontal asymptote is on this side, but it's still y equals 0. So there is our graph of an exponential function. Well, I would like a better example of a graph, right? That one I've just shown you, but how do we actually go about, really sketching one? So let's take as an example 2 to the power of x. I'm keeping the, to make calculations, at least in my brain, easy. What you would do is you'd set up a table of values and you'd find what the equivalent, essentially y coordinate would be for any given x. The choices of x are a little bit different than your typical, -3, -2, 0, 1, 2, 3, that kind of choice. A little bit different, but only a little bit. We're going to start with these guys and finish with them. That's pretty standard. So what about this fella? Well, 2 to the power of x is 2 to the power of -3, which is 1 over 2 cubed. And this time I am not going to do decimals. That's the little difference. I'm going to leave them as fractions. So this is 1/8. If you do this one, you can trust me and check it, you get a quarter. This one, you get a half. Then you get this guy, 2 to the power of 0. And hopefully you remember that one. It's 1. Then 2, then 2 squared, then 2 cubed. And for these x's, these are the corresponding y coordinates. So you go here. I know this is white paper. Can you pretend it was square paper? And you would go -3, -2, -1, 0, 1, 2, 3. Looks like I need 8. So 1, 2, 3, 4, 5, 6, 7, 8. So now I just plot the points. -3 is an eighth. Well, if that's 1, that's 2, that's 3. An eighth would be almost at the bottom. Then a quarter would be a little bit better. That would be a half. This would be 1. Then you'd go 2. Then you'd go 4. And then you'd go 8. And then you would join them together. And there you are. That's how you do it. Now, if you wanted to do a more complicated one, so suppose I have a function 1.3 times 0.5 to the power of x. Suppose I wanted to do that one. Then you'd set up the same values that we did before for the x's. So you'd go -3, -2, -1, 0, 1, 2, finally 3. And for each value of x, you would evaluate using this. Now that's a little bit messy, so let me try and show you if I can how we could do that on our TI-84. Okay, so what we're going to do is we're going to use our TI-84. So what you can actually see that on the screen. I'll just check. There, that should be it, right? So the function, you go and you type it in here. So you go 1.3 times, put a bracket around it, 0.5, close the brackets, to the power of x. And then you go to table setup, which is here, second table setup. And you make sure that this variant one, which is essentially the x, is now on ask. You can then do second table. And now you can type in -3, -2, -1, 0, 1, 2, and 3. And I will be writing those answers down, and we will try our best to plot them as accurately as we can. And I'm essentially just rounding all these answers off to one decimal place. And that's it. So stop sharing that. And there we go. So you imagine that we have square paper again. And it looks like the biggest number I need is 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, -3, -2, -1, 0, 1, 2, 3. And if you plug in -3, you get what? 10.4, which is about there-ish. Then 5 and a bit for the next one, which is about here. 2.6. Well, that's 1, that's 2, and that's 3. 2.6 is about here. And then you get 1.3. Now you notice it didn't cross the y-axis at 1. If it had been 0.5 to the power of x, it would, but this guy here kind of changed that. And 0.7, 0.3, and finally 0.2. And then we do our best to draw our guys. And in this case, you might be asked what the domain is. And if you were, I hope you would realize that it is all real values. The range, well, in this case, the range is still 0 to infinity, but you never get to 0. Have you noticed that these values get smaller and smaller? And you might say, well, what about that 1.3? Won't that make maybe the horizontal asymptote a little bit different? Not really, because 1.3 times a tiny number is still a tiny number. And this one doesn't have any x-intercepts. So the answer would be none. It does have a y-intercept, but it's not at 1, as it typically would be for a basic one. It's at 0, 1.3. And horizontal asymptote is at y equals 0, amongst other things. And that is how you would do a sketch of an exponential function using a table of values. And so we've essentially covered what is an exponential function and the graph of an exponential function. And at this point, that's where this is going to stop.